So, welcome, guys. I'm here for the next hour. My name is Frank Kane, and I'm here to talk about building recommender systems with machine learning and AI. That is the title of a course that's available on Manning.com's live video platform. Ooh, I can show it to you, actually. Let's take a look at my website here. And yeah, this is basically a very comprehensive course about recommender systems. It's really my passion. This course is really a labor of love. It's not my most popular course, but it's the one that I'm most proud of. And the reason is because recommender systems is really how I spent my career, or most of it, when I worked at Amazon.com and IMDb.com back in the day. So, this field changed my life, and the work that I did on it, I think, changed a lot of your lives too. Recommender systems, you see them every day, right? Go to Amazon. People who bought also bought. They're always recommending stuff to you based on your past purchases and things you've looked at. And that same technology is what powers ad targeting today. So, or personalized search, even. When you go to Google and search for something, recommender systems are under the hood there, trying to personalize those results for you. So, I'm honored to have been part of the in the early days of developing this stuff and actually rolling it out at Amazon, as far back as 2003. But yeah, we're talking about this course that's available on Manning, the live video platform. And just a quick plug for live video here, if I could. The thing that I really like about this platform is it's not just videos. You can actually watch the video, sure, but they also have the transcript over here on the right too. So it's kind of the best of both worlds of video and books, which I really appreciate. This might sound weird because I make training videos for a living, but I don't actually like learning from videos very much because it's so hard to get to the information you need. I don't want to watch a 20-minute video to find the 10 seconds of information that I actually want. But the beauty of this live video platform is that you got the text right there, so you can actually, scroll through it, jump to the spot that's interesting for you, and it's a lot easier to navigate that way. And I think that's a really innovative thing that Manning has done, and I'm starting to see some other platforms rip that off too. So if imitation is the highest form of flattery, well, you've been flattered. Let's go back to my main camera here. What brand of hats do you wear? Hey, I'll take any questions here. This is Q&A. It's supposed to be about recommender systems. We can talk about hats. I'm cool with that. Actually, I don't know. There's a website. I haven't got these back I haven't bought any in a couple of years, actually. I think this one, I don't remember. There's a website that's based in California. They have another one in England where they get their stuff from. Gosh, I wish I remember where I got it from, but on the internet is the short question. Not from Amazon, though, which might surprise you because I worked at Amazon for a long time. But these flat caps are kind of hard to find, at least good ones, So I actually started wearing these when I was at Amazon. It was kind of like my trademark thing while I was there, and I just kind of stuck with it. And to this day, it's sort of what I'm known for as an online instructor. So, we're going to talk about career tips later on in this stream, or at least I want to. I hope you ask some questions about that. And one of them is to have, sort of a distinctive personal brand, have something about yourself that's memorable. And for me, that's these hats. So, yeah, I really wear them every day. Cool. All right, let's get started and talk about recommender systems, guys. So let me give you a little bit more about my bio, and we'll open it up for questions. And if there's no questions from the audience here, I have some frequently asked questions that I can go through as well that I'm prepared to talk about. And we can also go through some code and actually see a real working recommender system in action. So we got plenty of material to fill up this time, I think. But yeah, just to tell you a little bit about me first, let's talk about me. My name is Frank Kane again. I am the president of Sundog Education. And these days I earn a living by making online video courses on platforms such as Manning. Before that, though, I spent 9 years working at Amazon.com. Started there in 2003 as a senior engineer, software engineer. And when I started there, they threw me into what they call the personalization team. This was the guys that were doing personalized recommendations. People who bought also bought. And back then, they didn't really call them recommender systems. It wasn't really a thing yet. It was just algorithms. It was programming more than anything. So we were kind of like blending these fields of data science, although it wasn't really called data science back then, software engineering and system engineering at very large scale and distributed systems to try to compute these recommendations for our customers, at least on a daily basis, and serve that in real time, to thousands and thousands of transactions per second. It was an exciting place, and kind of learned by getting thrown into the deep end of the pool there, But I managed to swim, thankfully, and worked my way up to senior manager by the time I left there. By the time I was done with my career at Amazon, I was actually running the engineering team for IMDb.com, which is a big movie website that's a subsidiary of Amazon, lots of fun there. Like it's just as fun as it sounds. um, but after 9 years, my family just couldn't take the weather in Seattle anymore, so we packed up, cashed out, and moved to Florida. That's where we are now, and I've been working for myself ever since, making courses for you. So that's my expertise in recommender systems. I didn't just do recommender systems at Amazon, but it really was the focus of what I did for most of that time. So between recommender systems and content optimization and, larger scale system engineering work. But personalization was always what it seemed to come back to for me. Even at IMDb, we had a movie recommender system, and you'll see the DNA of that experience in my course here because we lean heavily on making movie recommendations in this course about recommender systems because there's some really fun data sets out there to play with on that. Hey, we've got a question, and it sounds like a hard one. How can you determine the minimal size of previous information needed for a recommender system to be effective? Does it vary by application or platform? Yes, it varies. It varies very widely. There's no real set answer to that. You kind of have to experiment with it, to be honest. There's no formula because it depends a lot on the sparsity of that data, right? It's not just the quantity; it's how sparse it is, and that's what's different about recommender systems. It's not like normal machine learning where you have a complete set of training data. Like, for example, if you're trying to train a system how to identify a picture of a cat, right? You throw a ton of pictures of cats at it that have, every pixel in the image filled in, and you can train this neural network to figure out what a cat looks like, right? With recommendations, it doesn't work that way. Because a typical person, let's say you're recommending movies. Let's stick with that example. The typical person has not seen every movie in the world, right? I don't think anybody has. Well, I know one guy who has, my old boss at IMDb, Carl Needham. I think he's actually seen every movie. But for normal people like you and me, by and large, we've seen a very teeny percentage of all the movies in the world, right? Same idea holds true for Amazon. Like, you have not bought every item on Amazon. That is actually impossible. You've only bought a small amount of them, or you've even viewed a small amount of them. So this is what we call a sparse data problem. So the amount of information you need depends not only on the quantity of your data, but also on how sparse that data is. So, if I have, 5 million data points that people have bought the same 3 items, but I don't have any data points for like the other 10 million items in your catalog, that's not going to be helpful, right? So it's this balance between quantity of data, the sparsity of the data, and also the quality of the data as well. That plays a big role too. Give you an example of that. The best recommendations you will ever see are based on purchase information. And this is really the secret of why Amazon's recommendations have always been so good, because they can use data about what people are actually spending their money on to power and train those algorithms that they have. And there is no bigger reliable signal of interest than someone shelling out their cash and saying, I want to spend my money on this thing, right? That's a very hard thing to game. It's a very hard thing to fake. Very, very high quality data, right? So if you have a lot of purchase data and it's not sparsely distributed, that is the ideal situation. And that's the situation that Amazon is in, so a big part of why their recommendations are so good is just because their data is so good. In contrast, if you have click-based data, that can be very sketchy, right? If someone's clicking on something on your website or viewing something on a website, you don't even know if that was a person looking at it. It was more likely a bot of some sort or a web crawler or something like that. And just cleaning that data and making sure that data is actually human beings expressing real interest in something can be a real problem. Even in the world of purchases, there are data quality issues to be contended with. A good example is institutional buyers. So you get these people that are buying things for their company or for their institution, and they're just buying things en masse for this like huge organization of thousands of people. And to your systems, this looks like one person buying like everything on the planet. And that person ends up carrying an inordinate amount of weight in your algorithms as a result. And it doesn't really have any meaning to it because you're not really getting information about an individual's interests. You're getting information about this organization's interests. So yeah, it's a very long answer to your question. I'm not sure how to pronounce your handle there, but you know what I mean, right? The answer is no. That's the short answer. There is no formula. There's no set way to figure it out. You just have to experiment, quite honestly. The way that you really approach developing recommender systems is to just try different things and run A/B tests on it. Yeah, let's talk about that. So how do I evaluate a recommender system? That's a huge portion of this course, actually, because it's not at all obvious. There's a lot of ways to do it. So a lot of people in the research community want to evaluate the quality of their recommendations offline, right? Because they're in research. They're not actually going to be deploying this to a real world system. So they can't test it out on real people. So what do you do? Well, one thing you can do is measure the accuracy of the recommendations. And you can do that by saying, okay, I predicted that this person would rate this thing 4 stars. In reality, I know they rated it 3 stars, therefore my accuracy is, 1 out of 5 off, right? But that's kind of a sketchy way to evaluate things because the purpose of a recommender system is not to predict what you would have rated something you already saw. You're trying to get new things in front of people that they haven't seen before, or maybe they have seen it, but they didn't know they wanted it yet, right? So, really, the purpose of a recommender system is to show people things that they didn't even know they wanted yet, to read their minds, if you will. And that's why it's such a cool field. And that's a very hard thing to measure without getting real people in the loop. So, in practice, when I'm developing a recommender system and I want to know if it's good or not, the first thing I'm going to do, and we're going to do this when I go through the code walkthrough, is try it out on myself. I'll throw my own personal data at it, see what recommendations it gives it back to me, and I'll say, well, does that make sense? Does that actually reflect my interests, or is it a bunch of random crap that is irrelevant to me? And that's kind of the first line of defense on figuring out subjectively if I have a good algorithm or not, or if I have enough data, or the quality of my data is sufficient, right? The next step would be to try it on some other people, get some friends, get some of your office mates to say, hey, try this recommender system, see what the results are like for you. Do you think they're good? Do you think they're bad? Just get some qualitative feedback. I mean, the quantitative accuracy metrics are good and all, but they're just a very rough guide. You have to get it in front of people to really evaluate it. And the ultimate test is going to be getting it out there in a live production setting in a controlled experiment, in some sort of an A/B test, right? So if you have an existing recommender algorithm and you want to try a new one, you try the new one at 10% and you measure its results, make sure that it's not, doing something terrible to your revenue. And if it looks positive or at least even, ramp up that percentage over time of how much the new algorithm is getting exposed. And eventually you'll have enough data collected to actually know for sure if your algorithm is better or not. Whew. Yeah, again, great question with a really long answer and not a very satisfying one, I'm afraid. It is a hard problem to know, do I have good enough data? Do I have enough data? And is my algorithm good enough? This is really what makes recommender systems hard and interesting, in my opinion. Cool. Where were we? So yeah, keep the questions coming, guys. Definitely keep an eye on the chat here for anything you guys are asking. But I do have some frequently asked questions here. If I'm honest, the most frequently asked question I get is, "Can I get your course for free?" The answer is no. The other question I get is, "Will you do my homework for me?" Again, the answer is no. So we got those out of the way. But after that, I get good questions on this course by and large. One of the ones I get is, what are the prerequisites? Prerequisites. That's a hard thing to say. For getting into recommender systems. A lot of people, they'll stumble across this course. They'll say, "Ooh, that's cool. I can read people's minds with computers. I want to learn that." But you do need some background before tackling this stuff. Recommender systems is really a specialized subset of machine learning that deals with sparse data like we were talking about. And as such, it helps to have a background in machine learning first. And before you have a background in machine learning, it helps to have a background in Python and linear algebra, right? So you want to make sure you're coming into this with at least some computer science experience, at least some mathematical experience. Like, we're talking high school level math here, nothing too fancy. But you need to know how trigonometry works at least. One of the common metrics that we use for how similar things are is the cosine metric. So at least know what a cosine is, guys. At least know what multiple dimensions are. These are important concepts for recommender systems. So if you have that under your belt, you're in a good starting point. If you do have some CS, some programming experience, you can probably take this course successfully. It would be even better, though, if you had some of the basics of machine learning under your belt first. And I do offer a more general machine learning and data science course also available on Manning Live Video. Probably a good place to start if you haven't dipped your feet into the machine learning waters quite yet. And yeah, Python programming, obviously a good thing to have. I do include sort of a primer in Python. So if you do have an existing programming experience and you think you can pick up Python pretty quickly, I'll help you do that in this course. But obviously, if you know Python ahead of time, that also helps as well. But beyond that, I try to keep my courses as accessible as possible to people. I know they go out to a very wide audience with a very wide, diverse range of experiences. So I want to make sure people feel successful in them, right? So I try not to dive in too deep into, hardcore algorithms and fancy mathematical notation. I try to explain things in human terms as much as possible. Could I please share my machine learning course link? I like that question. Let me see if I can find it real quick off on the side here. I'll just go to the live video page on Manning, and once I find it, I'll switch my screen to it. Yeah, there it is. So apparently it is manning.com/live video/machine learning, data science, and deep learning with Python separated by dashes, but it'll be a lot quicker to just go to manning.com and search for Frank Kane and you'll find that course. But thanks for asking that. Appreciate that. Cool. Hey, we got another question. Abna Bulsi bought 4 of my courses and you really recommend them. I see what you did there. You recommend them. Good choice of word there. Thank you. I really appreciate that. That's great to hear. It's, if you look at my courses and their reach around the world, I've had over 500,000 people take my courses around the world, and it is mind-boggling the impact that's having. It's really a humbling thing. If you picture the biggest football stadium in the world could not hold all of those students. So the power of online education is just really amazing, and more and more people are discovering that now that we're stuck at home. So it's good that we kind of know how to do this now. We can actually share knowledge this way. Can you Mr. Code2K, can you recommend large public data sources that are available online to play around with? The UCI data repository, if you Google that, is a great source for free open source data repositories. The really big ones, if you go to AWS, I don't have the link offhand, but if you search for it, I'm sure you can find it. They have a ton of public data sets available there that are just hosted on AWS, within S3. And if you're actually, doing your machine learning on an AWS fleet of servers on EC2 or a SageMaker or what have you, it's very easy to access and pull in those large data sets that are hosted on AWS. So if you just search for AWS data sets, that'll bring you to it as well. What I use in the course is the Movie Lens data set. Let's talk about that. Let's go there. This is a good segue to that. So if we go to grouplens.org, this is kind of my favorite data set. And they have a wide range of sizes for you to play with. So a good technique when you're developing machine learning algorithms or recommender systems is to start with a small data set and work your way up to larger data sets. That way you can experiment on your own local PC or a single host in the cloud. And, don't start to invest in more and more of a larger cluster until you're confident that you're ready to do so. So if you go to data sets here, this takes you to the Group Lens data set. This is called the Movie Lens data set. And what it is a repository of movie ratings that people have made. I can show you what that looks like if we go to movielens.org. It's kind of like Netflix. They show you a bunch of movies and ask you to rate them, or at least how Netflix used to work. They don't actually do ratings anymore at Netflix, do they? But back in the day, this is how Netflix worked. So they show you people a bunch of movies and they ask them to rate them between 1 to 5 stars. And they've done this to actually thousands and thousands and thousands of people over the years, and they have actual real data on movie ratings that you can play with. So one of my favorite data sets, just because it's fun and because I like movies. I worked at IMDb. What can I say? But it's also easy to understand the results intuitively, right? So if you put in your own set of data of what movies you've rated and what movies you've enjoyed, getting back predictions of what movies it thinks you might like that you haven't seen yet, it makes it real. It's very easy to understand that and interpret those results. But anyway, you can see they have a large set of data sets here to choose from. They have a 25 million row data set here for when you want to scale things up. And if you want to start small, this is what we do in the course to get started. There's a small 100,000 rating data set. Obviously, you're not going to get as good recommendations from a small data set as a big one necessarily. And also, these are a little bit out of date, these older data sets. This one was last updated in 2018. So if you want data about the latest Hollywood blockbusters, you're not going to find it reflected in this data. But it's recent enough that you'll still recognize the movies that are in it. So a lot of fun working with that data set. And we're going to do that shortly. Let me go back to the Twitch stream here and see what other questions we might have. Oh, gosh, you guys are asking all sorts of stuff. This is great. Abna Bolsi, you went there. How can you start applying for jobs to recommender systems? What is the number of projects needed before applying? Yeah, this is actually my next frequently asked question. You read my mind, and you just added one to that frequency of that question. So yeah, let's go there. Let me get a little bit of a swig here. It's just water, don't worry. So yeah, getting a job, getting a career, that's what we're all here for, right? So when I was at Amazon, I was what they called a bar raiser. And a big part of my job was hiring people and interviewing people. I actually had the role of having veto authority for new hires all across the entire company, not just in my own team. So I was sort of like this Uber hiring manager, if you will. I literally interviewed thousands of people while I was at Amazon and hired hundreds of them. So I know a thing or two about getting a job in this field. So, first of all, let me make it clear taking an online course is the beginning of your journey. You are not going to get a job just because you took an online course. You're not going to get a job because you got a certification, at least not in the United States, by and large. You need to show that you can apply what you've learned and actually build something with it. So, your question is actually very well thought out. You're asking, how many projects do I need? And yeah, your head's in the right place, you know? So, if I think about the recruiters and the hiring managers at companies like Amazon, and mind you, different companies, different countries are going to have different cultures and different standards, but I'm just talking from my own experience here. They're going to be looking for either someone who, just graduated from a college that they know and trust. If you graduate from Stanford, you're going to get job offers. That's just how it works. Or if you're from a, not so well-known university, they want to see that you've applied what you've learned at least. So one thing they'll actually do is go out to like GitHub and like look at places like Kaggle for people who are winning coding challenges. And if they find someone who's like, new to the field, but is really showing a lot of promise in what they're accomplishing online, they might get a call. And that's another tip too, by the way. These companies don't call them; they call you. If you apply to these companies, they get so many applications they don't even look at them. We literally did not look at them. You want them to find you, and to make yourself discoverable, you have to be out there online. You need to be contributing to open source projects. You need to be, doing stuff like Kaggle challenges. You need to be contributing to whatever you can, publishing your work. Just make sure that the work you're doing is, A, interesting, and B, discoverable. Brag about it on your LinkedIn profile. Make sure they can find you on LinkedIn. Whatever it takes, just make sure you have an online presence that makes it really easy for someone to find you if they're looking for someone who is dabbling in recommender systems. Because that's the beauty about this field. It is like the most important field of AI and machine learning out there, and people don't even realize it. I mean, I can't tell you how much of Amazon's money comes from recommender systems, but it's a lot. And the same is true of places like YouTube and Netflix, right? Google, right? These are the biggest employers and the biggest drivers of the global economy, and recommender systems are central to what they do. And most people don't even know what recommender systems are, which is my next frequently asked question. What the heck is a recommender system? We'll go there too. So yeah, just having some a body of work that you can put out there on the internet related to recommender systems is going to be important. For example, when I was developing this course, I needed to find a framework to work within for the course, and I came across this thing called an open source project called SurpriseLib, developed by a guy named Nicholas Hug, I think it is. And if I was a hiring manager, I would give this guy a call. I'm like, hey, you've demonstrated that you understand how recommender systems work. You've demonstrated that you can write good code that is actually functional. It's well structured. I want you on my team, right? So it doesn't have to be a lot of projects. It just has to be the right project, one that really demonstrates proficiency. Obviously, research stuff, if you can find a cool research paper in the field of recommender systems and implement that and publish that on GitHub or something, someone might find you that way as well. Obviously, it's always going to be better to get real industry experience if you can. So a couple of other tips. One, do some freelance work if you can. That's always a good way to, get some professional experience under your belt and to make some connections within the industry. Because again, it's about, you want to make sure they find you. And there's two ways of doing that. One is to, put out such an impressive body of work that they can't miss you. The other is to know somebody. And that's just the unfortunate reality of the job market. If you know somebody who works at the company that you want to work at, you have a huge advantage over somebody who doesn't. And you can get those sorts of connections by doing freelance work. So if you do a freelance job for some guy who works at a company, or maybe he goes and works for another company in the future, he might remember you and keep you in mind when he has an opportunity. So the other strategy too is to identify the company you want to work for, but maybe accept a different job to get your foot in the door, right? So case in point, my career at Amazon. When I started at Amazon, I had no experience in recommender systems at all, or machine learning for that matter. I was actually doing 3D graphics software. I was a video game developer before I went to Amazon. But they, just saw that I was doing a lot of really cool and impressive work and doing it single-handedly. And, they found me and got me there. But My job title when I started, like I said, was just senior software engineer. It was not data scientist. It was not, AI researcher. It was not, senior fellow or whatever you want to be aiming for. But that's where it led to, right? So the bigger point here is to be open-minded about the initial role that you take within a company. It's a lot easier to get a entry-level job, maybe doing something slightly different than what you ultimately want to do, and then transfer internally later on than to go directly for that job that you're aiming for, right? So think long-term. It's always a good idea to get your foot in the door however you can at a company that has the opportunities that you want. Cool. Feast of Stephen. Yeah, I did miss your question there. Thanks for pointing that out there. Once I buy a lawnmower, for example, I want to see other products that I might need relating to lawnmowers. Can a recommender system do that? Yes, that is exactly what a recommender system does. So you also read my mind about my next frequently asked question. And that is, what is a recommender system? There's a lot of question about what it really means. And I've actually prepared some slides on that. It's such a frequently asked question that I'm adding a new lesson to my course about this, and you guys are going to see it for the first time here in Manning World. So let me pull up PowerPoint here, and I will just walk through it for you. So a little exclusive here for you. Let me switch over to my monitor. Yeah, there we are. So yeah, what is a recommender system? Let me get my PowerPoint deck up here. And it's really more about what it is not. The biggest misconception that people seem to have about recommender systems is that if I can put the word recommend into a problem, then I want a recommender system. No, that's not the deal. A recommender system does not just recommend arbitrary values for a problem. That's more descriptive of machine learning in general. Recommender systems are much more specific than that. So again, some examples of what it is not. If you want a system that recommends prices for a house that you're selling, that's not a recommender system. That's machine learning. A system that recommends whether a transaction is fraudulent, not a recommender system. That's a whole other discipline. Those are just generalized machine learning problems, and you use different techniques like regression or deep learning or XGBoost, for example. If those are the sorts of problems that you're after, you just want general machine learning, not recommender systems. What recommender systems is a system that predicts ratings or preferences a user might give to an item. So going back to your example of a lawnmower there, I want to be able to predict, would I like, I don't know, what's related to a lawnmower, a weed whacker, right? Would I be likely to purchase a weed whacker given that I bought this lawnmower? That's an example of a recommender system because I'm predicting that I have a high likelihood of purchasing that weed whacker or a high likelihood of rating it highly if I see it. And what a recommender system does typically is not predict a specific thing. It's trying to, again, read your mind to an extent. So the way a recommender system would work is that it would not just say, okay, given that I saw a lawnmower, what's the next thing I want to buy? It would look more holistically at your entire purchase history or your entire ratings history and produce a list of the top things that it thinks you might be interested in next. And if you recently bought a lawnmower and lawnmower-related stuff, then if a recommender system is working the way it should, you will see a list of lawnmower-related products at the top of that list. We call these top-N recommendations because the output of this recommender system is a list of, say, the top 10, top 20, top 100, whatever it is, items that you are most likely to like, given your past history. It goes by their names, recommender engines, recommendation systems, or recommendation platforms, all the same thing. So, for example, this is a recommender engine. This is actually pretty close to your example of a lawnmower. It's showing me recommendations within the automotive product category based on this wire stripper or something that I bought before earlier. And it's recommending a bunch of computer stuff apparently based on some computer components that I bought earlier as well. So that's the output of a recommender engine. It's trying to read your mind and predict things that you would be interested in that you didn't necessarily even know about until now. So I'm trying to... At Amazon, we call this incremental profit, right? So we're trying to introduce customers to things that they didn't even know existed, but once they see them, they're like, I got to have that, So that's really creating new value all across the board. Everybody wins on that, right? Like you get to discover these new things that are awesome that you didn't even know were there, that you love, and get them. And at the same time, Amazon makes more money. So everyone wins. Yay. So yeah, that's my short answer of what is a recommender system. And yes, your lawnmower example is a good example of that. So let's switch back to my main camera here. Cool. So basically, like market basket analysis. Yes, yes. Back when we used to just call those shopping cart recommendations at Amazon. Before market basket analysis was a thing. Yeah, same thing. That is absolutely a recommender system. That's a good question. Use IKEA. Cayenne03 says, "Hey Frank, any possibility of a new course about building end-to-end AI applications?" Ooh, so my data science course kind of does. We do have a final project in that course that actually gives you a data set about mammogram results, and you develop a system that predicts whether or not those results are benign or malignant. So, that's an example of one. And AI is among the many techniques that I ask you to apply to that problem. There's a wide variety of algorithms you can apply to these different problems. Deep learning, however, is usually always an option, and that's why Google standardized on it a long time ago, because it's this general purpose algorithm that you can apply to pretty much any problem that you can think of in the field of machine learning. Sometimes there are other algorithms that will beat it, like XGBoost is really cool. But this allows Google to focus on building out a framework and software around deep learning and leveraging that framework across its entire company and also its family of companies. So, for example, tying it back to recommender systems, YouTube, which is owned by Google, generates all of its recommendations for videos using this really huge deep neural network. And they're feeding in all sorts of crazy signals into it. And in my course, we go into the details about how that works because they were kind enough to publish that at one point. So it's really fascinating stuff. And they are using a special form of a deep neural network that can handle sparse data. That's what's hard about this because, again, you don't have this complete data set where everybody has watched every video. They've only seen a very small portion of all the videos out there. And figuring out how to feed that into the inputs of a neural network is really, really tricky. But YouTube figured it out. Amazon also figured it out. They've actually published a system called Destiny, DSSTNE, that can handle sparse data as well and produce recommendations. Cool. But anyway, yeah, I hear what you're saying. Cayenne03, a more strictly project-focused course would be cool. That is definitely something I want to do in the future. It's just been hard on the courses that I do because I tend to do these like really broad survey courses that cover like an entire huge field, and it's hard to find a single project that touches on every single aspect of a given field. But I guess you could say in this recommender systems course, kind of the unifying theme is making movie recommendations in a bunch of different ways. So, yeah, in a way. End to end, though, that does kind of imply, actually going all the way to the edge, vending that information to the end user. And yeah, this course does stop short of actually doing that. We do have a lecture on how to do it, but there's so many ways of actually serving data to the end user. You could use, SageMaker on AWS. You could write your own service from scratch using Java or what have you. You could just use like a NoSQL database that's really fast and store it all in there and like query that from your front end web servers. So, there's really, it's not a one size fits all sort of a thing. The way that you actually vend the recommendations you end up with to the world is going to depend a lot on your platform and the tools and technologies that your company happens to use. So, I'm kind of hesitant to teach you, one way of doing it because there's so many ways of doing it. And depending on where you work, it's probably not going to be the right way. So you kind of have to adapt these algorithms to the tools that you have at hand when you're in the real world. Cool. Got all sorts of questions. I love this. So Yuzakiya has another one. What do you prefer to code in for machine learning recommender systems? Python. Yes, I love Python. Back in the day at Amazon, we actually used C++ for everything, believe it or not. And that's just because we had such massive data that speed and efficiency was of the essence. But these days, Python seems to be pretty ubiquitous. I think it's kind of winning the war against R, quite frankly. And as a former software engineer, I want something that's a little bit more program-y. But Python really does seem to be the lingua franca of data science and machine learning in general these days. Everyone is using IPython notebooks, not just for like developing and prototyping things, but also for developing production systems now. If you use Amazon SageMaker, I've talked about that a few times now, but it's a really cool system. The interface for that is a IPython notebook. So it's really kind of hard to be in the field of machine learning and data science and deep learning without knowing Python these days, quite frankly. So I do believe Python's where it's at. And I don't really have a horse in that race. That's just my assessment of the industry right now. Cool. All right. What else we got? Yeah, we kind of touched on some of those other questions already. So some other frequent questions that I get are, how does deep learning work into the world of recommender systems? And I touched on that when I talked about YouTube. It is one way to do it, But it's not the only way to do it. And I don't know. Like I said, deep learning is just sort of like this ubiquitous hammer that people are hitting every nail with. It is a valid solution to pretty much any machine learning problem. And if you have specialized versions of deep learning networks that are tailored for sparse data, they can work for recommender systems as well. Netflix has done it. YouTube has done it. Amazon has done it. But there are simpler algorithms out there that I think personally work just as good, maybe even better. Specifically, there's something called collaborative filtering. And let's talk about that. That's actually the code example that I'm going to go with here. So let's actually dive into that. We'll start with some slides. So let me find where that is first. So basically, there's two different kinds of collaborative filtering algorithms in the field of recommender systems. There's user-based and there's item-based. The easier one to understand at first is user-based. So I'm going to start with that one. So let me pull up the slide here. Man, I really need 3 monitors. All right, there we go. And now I need to pull up the PowerPoint window again. Okay, cool, we're good. So this is kind of like old school recommender systems, and it still works today, guys. Gosh, I think my NDAs have expired with Amazon. Technically, I probably could tell you what they're really doing, but I'm not going to. It would still probably, get somebody in trouble. But I will just say these algorithms still work, okay? I'll leave it at that. So user-based collaborative filtering, how does it work? This is like not really how we do it, but it's like step 1 in understanding it, okay? So the idea behind user-based collaborative filtering is pretty simple. You just start by finding other users that are similar to yourself based on their ratings history. And then you recommend the stuff that they liked that you haven't seen yet. Got it? So let's say we have Ann and Bob here. Bob's a pretty edgy guy there. I like his hairdo. He's been self-isolating for a while, apparently. Got desperate for a haircut. Oh, God, I got to stop. So let's say that Ann and Bob here both loved the first Star Wars movie. Who didn't, right? And Ann also watched the next Star Wars movie, Empire Strikes Back. But somehow Bob lives under a rock and he's never heard of Empire Strikes Back. He hasn't seen it yet. So obviously, the obvious recommendation for Bob based on that is The Empire Strikes Back. It seems obvious that you would recommend that because Ann loved the same movie that Bob loved. Ann loved The Empire Strikes Back. Therefore, given that Bob is similar to Ann's interests, we can project Ann's interests back onto Bob. Does that make sense? And to make that a little bit more formal, we can construct this matrix. So to do this, to actually conduct user-based collaborative filtering, the first step is to collect all the data you need. And that's going to be a table of all the ratings for everybody in your system. And you can think of this as a 2D array with movies on one axis and users on the other, like we have here. And ratings are going to be the values in each cell. So these are like 5-star ratings that we're seeing here. So we can see in this example that Ann loved both of the first Star Wars films. Bob only saw the first one and loved it. And they each saw other stuff as well that they don't have in common. So Ann might enjoy Indiana Jones from the looks of it, since she has that connection to Bob through Star Wars. So it's not too much of a stretch to imagine this data as describing vectors for each user in an item space. Okay, stay with me here. Now, if these were the only 5 movies in existence, we could describe Bob with a 5-dimensional vector of 4, 5, 0, 0, 0, and Ann with 0, 5, 5, 5, 0, where 0 indicates a missing value. So that gives us what we need to compute the cosine similarity score between any 2 users, okay? Basically, you view these rows of ratings as 5-dimensional vectors, and you just compute the angle between them in this space of movie ratings. Okay, it's a little hard to wrap your head around, but that's how the math works out conceptually. So now you can build up another 2D matrix, one that maps the cosine similarity score between any 2 users in our system. So if our only 3 users are Bob, Ted, and Ann, maybe it would look like this. And take a close look so you can understand what's going on here. This just all falls out of the algorithm for measuring cosine similarity, but you can see that it makes intuitive sense looking at the results. Everyone is 100% similar to themselves, of course, so you have that line of ones going across the diagonal there. If you look up Bob's similarity to Bob, you get 1.0, and that's going to be true of anybody, right? But Bob and Ted have no movies in common at all. So if you look at that bottom matrix there and you look up Bob and Ted, you get a 0 because they have nothing in common. Now, there is some symmetry there. The combination of Bob and Ted is the same thing as Ted and Bob, right? So like you actually only have to compute half of this matrix in practice, which is a nice little optimization. So let's say you want to generate recommendations for Bob now. You can use that handy matrix that you pre-computed to quickly look up how similar he is to everybody else. And then you can sort that list by similarity scores and pick off the top 10 neighbors from that list. So it's very easy to say, okay, Bob, what users are most similar to you? Pull that off and get their set of stuff that they liked, right? So in this case, you'd end up with Anne at the top of the list, and you probably discard Ted because you'd probably have some minimum similarity score threshold that you'd filter people out at. And you also skip over the case of comparing Bob with himself, of course. Now, in a less sparse data situation, you'd have better results to work with besides just Anne, of course, but that's the general idea. You just look up the people that are similar to the person you're interested in, find the stuff they like that you haven't seen yet, and recommend that. It's just that simple. So once you pull all the movies that Anne and everybody else from Bob's top N users similarity results gives you, you can consider those candidates for recommendations. So in this example, Anne would be the only user who is similar enough to Bob to make the cut, but if there were other users that you found, you might throw their ratings into that pile of candidates as well. You would then score those candidates. You need to figure out which of those recommendation candidates are the best ones to present to Bob. And there are different ways of doing this. Again, it's sort of an art to this, as not so much of a science. But it seems reasonable to take the rating that's assigned to each candidate as part of it, right? So if you want to recommend things that similar users loved, you don't want to recommend the things that they hated. So you want to weight how highly they rated those items when you're scoring those recommendation candidates. So one component could be some sort of normalized rating score there. Maybe you translate a 5-star rating to a 0 to 1 range just so you can scale everything properly. And you should also take the similarity with the user who generated those ratings into account as well. So maybe you multiply that rating score, that normalized rating score, by how similar Bob is to Anne. And you can also scale that to a 0 to 1 range to make it comparable as well. And if you multiply those together, maybe that's a very simple scoring algorithm you could try out. You might also encounter the same movie appearing more than once in that list of candidates. So if we had more than one user that was similar to Bob that liked the same movie, you might want to strengthen that relationship because you're getting that additional signal from more people saying, yeah, it's not just Anne that liked this movie. These other people liked it too. It's probably a really good recommendation. So there's a lot of variance on how to do that. I'm not going to get into it now, but again, there's sort of an art to this and a lot of experimentation that goes into making it all happen. So cool. So that's user-based collaborative filtering in a nutshell. And let's look at some code. And first, let me check the questions here to see if there's any new things here. How about adding a mood feature to recommend a movie to somebody? That's actually a really good idea. There's been a lot of research and stuff like that. So yeah, you can use other signals and not just ratings data to feed into your recommendations. We call this hybrid approaches, hybrid algorithms, where maybe you're mixing in both behavior information from what people bought or rated together with intrinsic values, intrinsic things about the things that you're rating, right? And if you had information about the mood of a movie or the genre of a movie, for example, the category, the director, these are all valid things that you might throw into the mix. So we talk in the course about content-based recommendations, and that's how that works. We're not looking at user behavior data in that case. We're just looking at attributes of the things that we're recommending themselves. Mood could be one of them. Mise-en-scène is one of the things that we actually do as an exercise in the course, where we're actually looking at the pacing and the editing qualities of a movie to get a feel of how exciting it is. Turns out it's not a very good signal, but it's a good idea. It's something to try out. And it's actually really good when you have a sparse data situation, right? So if you find yourself in a situation where you don't have enough behavior data to produce good recommendations on their own, augmenting that with content-based recommendations in a hybrid engine can make up for that sparsity sometimes. So even if you don't have enough users in your system to make a good recommendation, sometimes you can just say, well, Bob likes science fiction movies. Let's throw in the top science fiction movies into his recommendations as a last resort. Perfectly reasonable thing to do. In fact, that's probably a good recommender system right there. So good question. So let's, I think I have some code here for a user-based recommender system here. We can actually go through. Doing good on time here. We're going to fill this hour, I think. And let me make sure I have that up. Yeah, here we are. So let me go back to my other screen here. So surprisingly small amount of code, right? This is actually a working user-based recommendation system. And it's this small because we're using existing frameworks and libraries and other code modules that I've already written. But I'll walk through this as much as I can in the next 10 minutes anyway. I want to leave an extra 5 minutes at the end for any last questions, of course. And to talk a little bit about item-based filtering. excuse me, as well. So this is a front end for user-based recommendations. Let's just run it as a first step. See what it does. Work backwards from that. So I'm just going to run it. Here we go. My head's in the way here. I'm going to have to move this window over. This ran a lot faster when I wasn't streaming stuff. We'll let that go there in the background. But let's look at the code here. So what it's doing, we'll skip this definition for now. This function here. Oh wait, it's almost done. It's almost done. Such suspense. I want that thing to be done. All right, it's so close. I'll just keep talking. All right, so we start off by seeding our random number generator. There we go. With a consistent seed, so we get consistent results on each time that we run this, so we can actually compare the results, apples to apples as we make changes to the algorithms or changes to the parameters. And that's another thing too. Just like with any machine learning algorithm, your choice of hyperparameters makes a big difference. Kind of the dirty secret of machine learning is that it's more about tuning the knobs and dials of an algorithm just through trial and error, through experimentation more than anything else. A lot of that can be automated even. So, but anyway, let's walk through this code. We do have some results here. Let me talk about that real quick. Let me move this over. So what this is doing is actually taking a sample user ID number 85 from the Movie Lens dataset, and I picked user 85 because he has pretty similar tastes to me. He likes science fiction movies, likes action adventure movies, and it's going to be making recommendations based on user 85's preferences. And what it came back with was actually a couple of different ways. So, okay, what's going on here? It's actually comparing several different algorithms here to each other. So that's why we're seeing a bunch of different results here. So the first one we're using is called user KNN. That's a user-based collaborative filtering algorithm. And it came back with some pretty weird results. Black Mirror, however, very good results. Galaxy of Terror, never seen that one. Android also sounds interesting. Again, this is an older data set. So what I'm seeing here is kind of an interesting set of results. Some of these I know are relevant, but a lot of these movies I don't recognize. That's not necessarily a good thing. You want a user to have some trust in the results that they're seeing from a recommender system, or else they're not going to click through and look and explore them. So again, there's sort of an art to this, right? It's not just about producing the things that I'm statistically most likely to enjoy if I were to actually watch them. I need to give people confidence that these are good recommendations, or they're not going to act on them. And if I see a bunch of obscure movies I've never heard of before, that's not going to give me a lot of confidence in this system. I want to see a few things that I know that I like in there. So again, there's more of an art to a science in this. And this is a great example of where a system that's being optimized based on offline accuracy metrics really doesn't produce good recommendations in the real world. We then compare that to item-based collaborative filtering, which we can talk about that. Let's go there. So user-based collaborative filtering, as you recall, the general idea is to find users that are similar to you and recommend the stuff that they liked that you haven't seen yet. Okay. Item-based collaborative filtering flips that on its head. And it says, look at the similarities between all the different items that you are recommending. Okay, so now take the set of all the items that I have liked, find the items that are similar to those items, and recommend those items. Okay, so it works the same exact way as user-based collaborative filtering, but it's focused on items instead of users. And the cool thing about this is that typically there are much fewer items in the world than users, right? So one benefit of that is that it's easier to compute because you have a smaller matrix to compute of similarities between items. So pre-computing all the item similarities, how similar is this item to this item, is going to be a much quicker computation than how similar is every user in the world to every other user. So that's one advantage. The other advantage is just the permanency of items. So people are weird. They're fickle beings, right? Their tastes change over time. Whereas items don't change. A math book will always be a math book, and it will always be similar to other math books. So you can get away with updating your similarities between items much less frequently than you would for users. So lots of advantages to item-based collaborative filtering. Although in this case, the results weren't all that great either. Again, we got Galaxy of Terror, which and Android, very similar set of results, but again, a lot of stuff that I've never heard of before. Master of the Flying Guillotine. I'm pretty sure that's a bad kung fu movie that I've seen on like really sketchy cable TV stations. To be honest, I think I saw that. I might have actually enjoyed it. So, but again, it's that issue of trust. You want to make sure that people aren't just seeing obscure things. There's ways of measuring that obscurity too. There's metrics like diversity and novelty that we talk about in the course, where you can actually get a quantitative handle on, just how obscure the things are that you're recommending, and you don't want that to be too bad. And then just give us a baseline. We picked some random results just based on what ratings are out there randomly. And interestingly, well, these actually aren't that bad. So, this tells me that these results that I'm getting aren't that good. Part of it, again, is because, we're dealing with sparse data. The other part is that it's a very small data set. So we're computing this on the 100,000 kind of like starter data set of MovieLens. There are much larger data sets out there that will give you better results. And you can see up here, too, we actually computed some of the RMSE and MAE scores. These are accuracy metrics. So again, what we're doing is looking at predicted ratings for every item versus actual ratings, and seeing how well those actually line up in the real world. And we measure that using these metrics of accuracy. But back to the code. So basically, what we do is we call this load MovieLens data function that actually loads up our data set. And again, we're using a third-party open source library called SurpriseLib to do the heavy lifting here. So it has a handy-dandy function for loading up the MovieLens data set for you. And that's actually calling out to our MovieLens module here that we wrote. There it is. And the guts of this code isn't terribly important. It's just parsing the MovieLens data set, storing it into a data set that we can actually feed into SurpriseLib. And it also has some useful things like finding out how popular each movie is, how often it's been rated, and we can use that for things like measuring things like novelty. Back to our bake-off code here. So then it constructs an evaluator class that we use throughout the course. Again, this is just a boilerplate framework that we use to run multiple recommenders in parallel and compare their results to each other. That's all that's going on there. The guts of that is in evaluator.py. All this code is provided with the course. So, the first lecture tells you where to download this from so you can go and play with it and experiment with it, use it for reference later on. It's all there for you as part of the course. And under the hood, that also uses an evaluation data class that, handles all the nitty-gritty of getting the various train and test sets that are associated with that. It also does something called leave one out cross-validation, which is sort of a cross-validation technique that's specific to recommender systems and top-end recommenders in specific. The idea there is that how do you measure accuracy when what you're producing is a set of the top 10 recommended things for a user? That's actually kind of tricky. The one way to do it is leave one out cross-validation. And the idea is that we pick one of those top 10 results, withhold that rating from the training data set, and see if we're actually able to regenerate that rating within our top 10 set that we come up with. Sounds like a really good idea in theory. In practice, that happens very, very, very infrequently. So it's actually a very difficult metric to use. But some papers use it in the research world, so we put it in there for completeness. Back to the source code here. So you can see here we're doing like a little bit of a bake-off. We're setting up a user KNN. That stands for user K nearest neighbor. So a fancy way of saying look at the K nearest users to user number 85 and recommend stuff that they liked. That's all user-based KNN is. It uses a KNN basic class as part of the SurpriseLib library to make life nice and simple. It's saying that we're using the cosine similarity metric when we're computing similarities between users, and this is user-based similarity. We add that into our evaluator. Then we do it again for item-based similarities. Same thing. Again, we're using cosine-based similarity as a metric, and in the course we go into a lot of other alternative similarity metrics. The only one I don't tell you about is the one that Amazon actually used. That's a secret. But the ones that have been published, I tell you about. And in this one, we're just saying user-based is false, which means that instead of looking at similar users, again, we're looking at similar items. We're looking at the items that you liked, finding items that are similar to those items, and recommending those to you. It's just that simple. And then for comparison, we have a random recommendation algorithm that just picks stuff across a normal distribution based on how often they're rated and recommends that to you. So the baseline that we used at Amazon was similar. We just compared recommender systems to top sellers. And that was kind of our baseline as to whether personalization was really happening effectively. You can show the same set of top sellers to everybody in the world, right? They'll get the same results. Your job is to do better than that. You want to tap into people's individual interests and show them things that they are specifically themselves uniquely interested in. And to do that, you need to outperform how well people respond to just a list of top sellers. And it's actually harder than it sounds. A lot of people like popular stuff, it turns out. So recommending top sellers is actually not a bad idea. It's just not a recommender system. It's not personalization. We then call evaluate on our evaluation class and sample the top 10 and print them out. And that's what happened in the output over here. So there you have it, a working recommender system in just a handful of lines of code. Obviously, there's a lot of support code here. There's the surprise lib library itself, which is a whole lot of code too. But actually implementing this stuff does not have to be hard. That's kind of the key takeaway here that I want you guys to leave with. And with that, we have 5 minutes left. Let me check for any more questions. Oh, yeah. Are there any other metrics for similarity apart from cosine that work well? Yeah, there's a ton of them. Pearson similarity score comes to mind. That's the main one. There's a few different flavors of that one, actually. But, not only do we talk about different similarity metrics in the course, we also talk about different algorithms entirely. So there's, techniques like singular value decomposition that actually work. If you use Apache Spark, for example, they use something called alternating least squares, which is a variant of that. Another approach uses something called matrix factorization. So instead of looking at similarities, they're actually trying to compute a matrix, so you can compute this matrix of users and items against to actually get recommended results and fill in all those missing sparse values. So there's a whole lot of ways of doing this. And again, there's more art to it, more of an art than a science to this, because there's just so many ways of doing it. And a lot of it is just creative thinking, kind of like thinking about what does the customer want to see, getting into the heads of your customers and making the right choices about how you weight things, the algorithms that you use, how you filter that data at the end of the day. So it's not all science, and that's what's kind of cool about this field. Great programmer. A couple questions here. Let's see if I can get through both of them. I got 4 minutes left here. Borg Major, I'm not sure how to say your username. I hope I got that kind of close. Have you ever used something like PageRank for the movie descriptions to find similarities? Interesting question. PageRank technically would not be a personalized algorithm, so I wouldn't call that a recommender system. But it could be a signal. It could be an input, right? So personalized search is a whole field of itself, right? So you could take PageRank and, sort results based on that, and then apply personalization on top of that to like sort of resort or optimize the order in which you're showing those results. That would be a valid thing to do. So yes, very closely related field. They can work well together. Great Programmer says, what does the system know about the movies other than the name, genre, actors, plot points? So the code we just looked at knows none of that. It knows the name just so it can display it to you, but it's not actually using that information internally. It's only using user behavior data. Hey, we have a winner for the contest. Woohoo! Jorda Heil Desma, congratulations. Anyway, but back to the question. That is just based strictly on ratings data and nothing else. So in the course, we do talk about content-based recommendations. And in this data set, we do know the genre. We know the title, obviously. We also have a link to IMDb as well that you can mine for further data. And obviously, IMDb knows everything about movies, the actors, the directors, plot summaries, reviews, whole world of data that you can get there, sort of like a second order of data that you can pull in. That's not actually part of the Movie Lens data set itself, but it shows you how to get there. So yeah, you can work all that information in as well. And again, these hybrid approaches where you work in behavior data and content-based information can work well, especially if you have sparse behavior data. Hello, Tutor Exilius. Thank you for joining us. I hope you will go back and re-watch this if you're just joining us now. We are just at the end of this stream where we've been talking about recommender systems. And I'm going to wind this up now. Again, thank you to Manning Publications for hosting me here tonight on Twitch. It's been fun, guys. I hope you've learned a thing or two. And stay safe. And again, you can enter to win a free live video. Check the comments there from Candace Senni if you want another chance to be a winner. Cool. So again, I am Frank Kane from Sundog Education, here on behalf of Manning Live Video. And again, if you want to check out our code on Manning, head on over to manning.com, search for Frank Kane on Live Video. And as you can see in the corner here, they have a special discount code for you, TwitKane40. Get a deal on this course and get it for a special price. I don't actually know what the price is, but it's a special price. So again, this course has been a labor of love. I'm very proud of it, and I hope you enjoy it. So take care, guys. I'll see you later.